by Jerome BUZZI and Ali TAHZIBI in the next days. So it is about unstable entropy.
So thank you. I'd like to thank the organizers for this exciting conference. And I'm very happy to be here in this great place. So we were asked to give a course about unstable entropy. So then we accepted. Then I realized that there was a lot of things that I didn't really know. So I tried to learn them in time for this course. So the goal of our mini course with Ali TAHZIBI is to introduce you to this notion, and which appears in several settings. And the ultimate goal is to study ergodic theory. So from our point of view, especially measures of maximal entropy, and then equilibrium states, OSRB measures. And one way that has been developed for some time now is this kind of, first you try to use the uniform behavior of your partially hyperbolic system. Okay, this is where unstable entropy appears. We'll see that it shares many properties with the entropy of expanding systems. Okay, and then you try to extend to go from this partial entropy to the full entropy. I mean, it's the same kind of strategy, let's say, than what Aaron was discussing before, in the sense that you have an object which is partially good, and you try to show that to extract information, let's say in general, about the full object. Okay, so today, so there will be 4 lectures. Today I will try to review some of the fundamental theory. Okay, then there will be 2 lectures by Ali, where he will develop, well, actually he will do some proofs, and he will explain how you can identify some geometric properties of the measure through a convexity argument that was used a lot by François, who once told me, you know, some people have made careers out of strict concavity. Okay, and then he'll tell us about some versions of the invariance principle. Okay, and there will be some application, and I will conclude by giving some application of this entropy or unstable entropy method to mostly expanding and mostly contracting diffeomorphism. Okay, so today it's really the basics. So it will be divided into two parts. The first part will be essentially Le Drapier-Yang theory, or some generalization, especially due to Aaron Brown. Okay, and the second part will be about the setting of when you really have uniformly expanding foliation. Okay, this is done in this is due in particular to Yang-Yagang and Hu-Hui, Hua, Yao-Xing, and Wu Yanshu. Okay, and here I put the main references, at least the main references for me. Okay, so what is the setting in this first part? Okay, so I will, so somewhere in the back there is Piecine theory. So we have to assume that our diffeomorphism is not only C1 plus some Holder continuity. Okay, we will deal with a compact manifold. we will consider an invariant ergodic measure, and we will have to make some assumption on the foliation. I will explain later. And the goal of Le Drapier-Yang theory is to estimate the entropy in terms of Lyapunov exponents and dimensions. And now what we want to do, this is this generalization, which is especially due, done in this paper by Brown, Federico Rodriguez Hertz, and I think it's Zhang. I don't know why I put a W. Where you look not only at the full entropy, but at the entropy inside some foliation. Okay, that's what we want to do. So what are these nice foliations that you can deal with? Okay, so in that paper, they define tame foliations, which I don't want to get into. So I will just tell you, give you a specific case, which is enough for our purposes. So first, you can consider a continuous foliation. So a foliation it's a partition into C1 leaves. Okay, and you ask some continuity transversally. Okay, this is expressed by this atlas. There are a lot of information in the slides. I will give the slides, but you're not supposed to read all of them now. Okay, so the first setting is the continuous foliation. The second setting comes from Piecine theory. So each time you fix some positive number lambda, okay, and then you look at the points that have orbits that converge exponentially faster than this exponent lambda in the past. Okay, this defines a partition. Piecine theory tells you that this is in fact a relatively nice foliation in some sense, okay, which is exactly this sense that I don't want to tell you about. Okay, in particular, for almost every point, the sets are immersed submanifold. Okay, and so when you vary lambda, you get finitely many such foliations, which are nested one into the other. Okay, and they correspond to the different Lyapunov exponent, but I don't want to write it now. So you have this, okay, and you consider, so here you have R distinct positive exponent, and it gives you R foliations from the strongest with the smallest leaves to the weakest, but still exponential. Okay, and for us, an admissible foliation will be an intersection of one invariant continuous foliation and one Piecine unstable foliation. Okay, and then it satisfies what they call tame foliation, but I don't want to go into this. Okay, so now I want to be able to define, my goal is to define entropy subordinate to such a foliation. So for this, I have to go back to the definition of entropy given some partition. So in general, if you have a nice partition, here this means countably generated. Sometimes it's called measurable partition. So it's written there, but I don't care now about the details. When you have such a partition, you can disintegrate your probability measure. Okay, it's a kind of conditional expectation, but at the level of measures. And this allows you to define the entropy given any such countably generated partition. Okay, here there is no assumption that the mean entropy is finite. Okay, and what is this formula? So you say that the entropy of your system, where you have your dynamics and the ergodic measure mu, here it doesn't have to be ergodic, well, it's the conditional mean entropy of your partition given its future. Okay, so that's the definition. Oops. Sorry. Okay, you can write this. Now, if you use the invariance of the measure, you can write it this way. This maps to this way. This psi plus is just this notation for the future, including the present. Okay, and then you see that since you condition by psi plus, you can add it on the left. It doesn't change anything. And so in the end, you get this formula. Okay, so it's you consider the conditional measure after this integration with respect to this key plus. Okay, and you consider the size of the atoms of the pullback of your partition psi plus. Okay, so it tells you exactly, well, that's a classical definition. That tells you, okay, what is in some sense, the number of choices that you would have to go to add one time when you already know the future. Okay, so this is, I have just, so now you say that the entropy of mu given a partition psi, which you have to assume countably generated just to be able to disintegrate. Okay, that's in the formula, is this quantity. Okay, I remind you the full Kolmogorov-Sinai entropy is when you take the supremum over all partitions. So all countably generated partitions. Again, I stress that you don't need to restrict to partitions of finite entropy. Okay, when the entropy is finite, you have extra good properties, okay, that I recall here. Like you have this other formula, which is always true even without the space being nice. And under the same assumptions, you would have this monotonicity property. Okay, and this partition with finite entropy, they are enough to compute the entropy, if you like, so, but you don't have to. Okay, two very easy, but maybe not so stupid example to understand that you have to be a bit careful when you're dealing with arbitrary partition, is that if you take as partition epsilon, the partition into points, then you see that since we are looking at an invertible system, a diffeomorphism, then this entropy will be 0 always, just because you're conditioning by everything, so of course. And if you take the trivial partition with just the full space as an element, then again you will have 0, just because this time you don't distinguish anything. So it's clearly not monotone, except when everybody is 0. Okay, so the goal so what we want to introduce is the entropy subordinate to a partition. Okay, the idea is that you want to measure what's going on inside the elements of the partition. Okay, so the definition is the following. You have one partition, which is you want to compute the entropy with respect to that. So you don't know if that partition eventually separates points. I mean, if it's invariant, for instance, it will not separate point inside an element of itself. Okay, so now you define the entropy subordinate to one partition. as the supremum of the entropy with respect to all partitions which are finer. Okay, so then you see that if alpha is less fine than beta, then the entropy are in the other order. It's a non-increasing function of the partition. Okay, and of course, if you take the entropy with respect to the point partition, then you have 0. Okay, since you have to be less fine. Sorry. I think no, it's the other way around. So if you take the entropy subordinate to the point partition, then you take the supremum over all partitions, since they are all finer than your. No, sorry. Sorry. So okay. So you do the exercise, and yeah, and you will see that for the trivial partition you get the full entropy because everybody is finer than this partition. Okay, and you get 0 at the other extreme. Okay, and then again you can compute using refining by partition with finite entropy if you want. So to get more feeling, you can do this exercise. You take a product system, okay, and you take as a partition this partition where you disintegrate just, how should I say, well, into this thing. So let's say these are horizontal sets, okay, corresponding to the first system. And if you do that, then, so with respect, sorry, it's eta here. So the entropy given that partition eta is 0, just because, yeah, now I am confused. Yeah, it should be eta. That's. Okay, so let me think what I'm doing here. Okay, so the entropy for the Kolmogorov-Sinai entropy for the product is just the sum of these two. If you condition with the entropy subordinate to eta, so then you have to look at partitions which are finer than eta. So it means that you will see what's going on inside these elements of the partition. So you see the entropy of the first system. Okay, but if you consider not the subordinated partition, but the entropy given that partition, then you find 0. Okay, for instance, so I mean there. Okay, any questions? Okay, and this notion is also contains a lot of things, in fact. For instance, you can check that it allows you to define the fiber entropy in the Abramoff-Rochlin formula for the entropy of an extension. Okay, so remember we record the entropy given a partition, the entropy subordinate to a partition. Our true goal is to define entropy subordinate to a foliation. So in dynamics, it's well known, the typical foliations are not usually measurable, like the unstable foliation, the Pesin unstable foliation of something with positive entropy is not measurable. So you have to do a little trick. Okay, this trick is this definition, which is to say that, okay, if you have a foliation, you will consider a nice partition which are subordinate to it in the sense that almost, if you take almost every point, the element of the partition, first it is contained in the element of the foliation. Then it is, in fact, open in that element of the partition. And finally, you want it to be bounded for the, let's say, also the intrinsic distance in this element. Okay, so you don't want to have, I don't know, points or something which would lose the memory of your foliation, and you don't want to have whole leaves. And now that you have this notion of subordinate partition, you can define the entropy subordinate to the foliation by playing again the same kind of game. Okay, so this is this h mu f of f. You take the supremum over all partitions which are subordinate to your foliation. Why not? Okay, and of course, you can write this definition for any foliation, but you will need some regularity to make it workable, in particular to ensure that you have subordinate partitions. And this is where we have to do this assumption of admissibility or, in truth, tameness. Okay, so then now let's, so after these many definitions, let's see what the theory actually says. So the first big thing is that, okay, as you could expect, but it turns out to be quite delicate, to see the entropy, you only need to consider unstable directions related to positive Lyapunov exponent. Okay, and this is so this is true for, so at the level of Kolmogorov-Sinai entropy, this would be saying that the Kolmogorov-Sinai entropy is already seen when you look at the entropy subordinate to the weakest Piécine unstable foliation, the one associated with the smallest positive exponent. Okay, so this is... this means the subordinated... Sorry, what was your question?
And both of them have foliation superscript?
No, oh, I mean, yeah, you can specialize this theorem, this statement, to the case where F is the trivial partition, and then you get the subordinated entropy to the trivial partition, to the trivial foliation. Okay, you go through the definition, and you see that it's just a complicated way to say Kolmogorov-Sinai. Okay, and in this case, this is for the left side, left-hand side, and the right-hand side then is not trivial at all. It's the Piécine unstable foliation. And so this was one of the maybe, well, at least given what was known before, one of the big steps in this theory of Le Drapier-Yang. I mean, the first joint paper on this was to see that indeed what you could think from a kind of absurd ideological ideas that entropy should come from a positive exponent, it works in this sense. That is the entropy, the Kolmogorov-Sinai entropy of a measure is the entropy subordinated to the Piécine unstable foliation. Okay, and this was extended then in that paper by Aronson and collaborators to the case where you consider the entropy subordinate to a reasonable foliation. Okay, then you... Okay, so to work on this, you have to know, as I said, that you have good partitions. Okay, and this maybe was first shown by Le Drapier and Streltsyn, okay, and then in some settings. And then the statement here comes from always this same paper, that there exists a good partition. So what is a good partition? So always countably generated, but then one wants it to be subordinate to the unstable, to this FU, okay, which is the joint of the foliation and the weakest Piécine foliation. So I remind you, it means that it reflects essentially the foliation. It's an open neighborhood, bounded open neighborhood inside each leaf. We want it to be increasing, so this means that when you apply the dynamics, you obtain a less fine partition. Okay, this is reasonable since we will be working inside the Piécine unstable foliation, so you expect things to expand. Okay, and finally, you want it to be generating so that when you let the dynamics act, you separate into points. Yes?
What are the hypotheses of this theorem? Is enough for it just to have a positive Lyapunov exponent?
No, well, if you don't have positive Lyapunov exponent, then the entropy will be 0. The unstable Piécine foliation will be the trivial foliation. So just this tells you 0 equals 0. So, yeah, but yeah, here we don't need. So in principle, it can be a way to show that everything is 0. But, okay, so now, so this theorem tells you that given an admissible foliation or tame foliation, then you have such a good partitions, and you take any one of them, it allows you to compute the entropy subordinate to the foliation. Okay, so this is, if you want to work, it's good to know that you can actually do it with any one of these partitions. Okay, so now let's explore, what we can say. So from first result, one can be formulated as a subordinate, as a kind of Brin-Katok entropy formula. Okay, so for this, I need to introduce F dynamical balls. You could think of them about like unstable dynamical balls if F was the Piécine unstable foliation. So these are defined in the natural way. So first you take the distance inside the leaves. Then you do what you're used to do with this distance now. So you define the dynamical distance to be the maximum distance between the iterates. And you do, then this is a distance. So its balls are the dynamical balls of Bowen and Dinaburg. But yeah, with this distance. And now, what you get from one of the things you get from this theory is this formula, okay, which tells you take a good partition that is provided by the previous theorem. Now you can, so it lives in the element psi of x, but psi of x is a neighborhood of x in the foliage, in the leaf. So the leaf also contains these dynamical balls. Okay, so you can compute their measures and ask how fast this measure decreases with n. Okay, and the answer is the subordinate entropy. Okay, so the case, if you take F to be the trivial partition, this is really a Brin-Katok. Okay, so now this is the, we really want to talk about exponents. So now you look at the exponent inside your invariant admissible partition, F. Okay, so you look at the distinct exponent. You have some number of them, which is called R, and each one occurs with some multiplicity, which are these M. Okay, so, which depends, R also depends on F, of course. Okay, so if you take a bigger foliation, less fine, then you have, of course, more, the spectrums are included into one another. And our remark is these Piécine foliations, they are, of course, related to the Lyapunov exponent. I said in a somehow very abstract way, there are finitely many such foliation given mu. Okay, it's very concrete. The value of lambda that gives you distinct foliations are exactly this Lyapunov exponent. And the smallest one corresponds to the largest exponent. Okay, and then when you consider the second exponent, you get a new foliation, which is less fine than the first one, and so on, until the last one, which this is this new U. Okay, and the dimension increases, the dimension of the leaves increases exactly by the multiplicity of the exponent. Okay, so a classical theorem for Kolmogorov-Sinai entropy is that if you have a C1 map of a compact manifold, then the entropy is bounded by the sum of the positive exponents with the multiplicities. Okay, so you would like to, do you have the same in our setting? Well, the answer will be yes. So if you consider now the subordinate entropy, so you don't see the exponent that may be outside of the transverse to the foliation. Okay, maybe some exponents are both along the foliation and transverse to it, but you don't care about that extra multiplicity either. You have exactly the same formula, but subordinating everything. Okay, and the extra thing is that the equality case, this is the strict concavity of the logarithm, okay, is exactly when you're absolutely continuous along the unstable refinement of your foliation. Of course, the entropy doesn't tell you anything about directions with zero exponent or negative exponent. Okay, so this was, So you notice that here, Ruelle-Margulis inequality was for C1. Here we are C1 plus Holder. So for the second part, the characterization, there are counterexamples. But for the first part, I don't know if there are. This is really, or at least for me, it's really a question. Whether for just the inequality, do you really need C1 plus alpha? Okay? Already you could ask, okay, let's take a continuous foliation invariant, okay, do you have real inequality for C1? In fact, the proof, both the Le Drapier-Yang proof for Kolmogorov-Sinai entropy or the proof of Aaron and the two other guys in the admissible situation gives you more. So it tells you how much the entropy. So remember, you have this strong unstable foliations. Sorry, this PSE unstable foliation from the one defined by the, so the one with the, which is the finest, defined by the biggest Lyapunov exponent, and then you increase by taking into account the second, the third exponent, you get foliations which are less and less fine, and so they are bigger, the elements are bigger, so their entropy can be bigger, and this formula bounds you, gives you a bound for how much it increases. Okay, if you want to compare, if you restrict to the, I don't know, the first two exponent, then you have already some entropy. How much does it increase? It's given by this formula. In fact, they have, I'm hiding things. Well, I'm hiding a lot of things. But all these results before, they come from this magic, well, they are contained in this magic formula that tells you that the subordinate foliation is exactly the sum of the Lyapunov exponent, Lyapunov positive exponent, times some dimensions, okay, which have some geometric meaning, I mean definition, which is complicated, but still they have geometric meaning, and this is really an identity. Okay, and this is true, you can apply it to F joint with any of the unstable foliation, and then you get expressions for all these entropies, and you see that their differences is exactly bounded, is exactly given by this with the number gamma, and this number gamma are less than the multiplicity. Okay, but at some point we will use that information one day. Okay, so that was for the, sorry, for the case of you want to compute you are in a somewhat general situation where you have your admissible foliation, so which is invariant and satisfies some regularity assumption, and then you have this very general and beautiful theory that gives you this information that goes much beyond Ruelle-Margulis inequality. Now we switch settings. We go to a much stronger setting where sorry, it's not, we will have a uniformly expanding foliation. Okay, not just admissible. So what is a uniformly expanding foliation? It is a foliation which is continuous, invariant, and which expands. Okay, that's natural definition. And so the motivation is the study in particular of partially hyperbolic systems, okay, that were already mentioned in the previous talk, where you have, so you have your partially hyperbolic splitting, which means that the tangent bundle has a dominated splitting, and you have some uniformly expanding bundle. I'm not saying this that so ECS is whatever it is. It can be also have some parts which are uniformly expanded, or maybe not. You don't care. Here you just want to assume that you have this uniformly expanding direction, which is strongest, which dominates the rest. And then it's well known that you have a strong and stable foliation tangent to it, which is unique, invariant. Okay, and it is a uniformly expanding foliation, very clearly. Okay, and this is what we want to talk about mostly. So there are some works, for instance, the paper by Marcelo and Yagang about measurable properties of center foliation. So here you see that we don't assume when we say uniformly expanding foliation that it is the strongest. Okay, but it is uniform. Okay, and so the name of the game now is use this expansion so that to try to get as many properties as you can, which are like, you know that for expanding map, you have lots of very nice properties, lots of things that are complicated in general, but that become simple, and this is what you want to generalize. Okay, so, sorry. So this is the purpose of this exercise. If you have an expanding map, then you know that the measure, for instance, that the entropy is upper semi-continuous. Okay, and the proof is quite simple. First, you deduce from the expansion that any partition with small diameter will be generating. And then this tells you that you can compute the Kolmogorov-Sinai entropy with respect to any partition with that small diameter. And now the entropy given a partition is continuous, is upper semi-continuous. Why? Because it is the infimum of this of 1 over n of these entropies of alpha n. Okay, and so it's an infimum of a family of functions, but these functions are continuous at each measure such that the boundary of the partition has 0 measure, just because the function that associate to a measure the measure of fixed set is continuous in the weak topology, or at least when the measure of the boundary is 0. Okay, so that's basic stuff. And the idea now is that actually this can be generalized to a uniformly expanding situation. Let's say if you think just a bit, it seems, yeah, you believe it. Now if you have to do the proof seriously, it's less, we'll see there are some difficulties, but it's true. Okay, so what was proved by Yagang and also by Hui and others is this thing that you have this upper semi-continuity both with respect, well, thrice with respect to the diffeomorphism, the foliation, and the measure. Okay, so for instance, now you can just fix the diffeomorphism. Imagine you have a partially hyperbolic diffeomorphism. You look at the foliation, the strong and stable foliation, okay? And now you take a sequence of measure, and you say that you get that the entropy subordinate to that to the strong and stable foliation is upper semi-continuous. Okay, then if you want, you can let also the partially hyperbolic diffeomorphism converge. Okay, it will force the C1 convergence of this diffeomorphism will give you the convergence in a suitable sense of the foliations. So you again have this semi-continuity property. So as I said, the exercise is very easy. So it gives you confidence that something like that should be true. When you want to do it, it's not so easy. Okay, the difficulty in this theory is that the computation of the subordinate entropy, essentially it means that instead of computing, for instance, the entropy of a fixed partition, so that you could, like this, use this obvious continuity, now you are conditioning with respect to another partition. So in this case of uniformly expanding foliation, you can use even simpler partitions, which are alpha here could be any finite measurable partition with small diameter, by the same remark as above in the trivial case. And beta is any partition like that, but then you cut it by local leaf. Okay, and it's proved that it gives you the subordinate entropy. But still, here, it's no longer just the measures of the element of alpha or beta or alpha intersected with beta. But if you want to apply this, you will have, okay, the boundary is everything. Anyway, it's much more, this is where there is a difficulty. Okay, so this is, if you look at these papers, you will see this is the point where it gets technical. It's to show that, okay, despite the fact that it still has this semi-continuity property. So one simple consequence of that is that the set, if you look at, so you have these subordinate entropy with respect to your uniformly expanding foliation, actually this supremum will be achieved. Okay, and the set of measures that achieve it will be a compact, so will be even compact. So it's a compact non-empty set just as a consequence of this upper semi-continuity. So you can consider this to be a measure that so these are the measures that maximizes the F entropy, okay? And what we will see, especially in the lectures by Ali, is that how you can, so you see, you have nice result about this UMME, okay, when you consider the strong and stable. And now this gives you a kind of foothold to try to study MME. Just like in the theory of rigidity of Gibbs U states, you know you have good behavior along the unstable, like here, and you try to extend it to the rest of the dynamics. Okay, and we'll see cases where it actually works. Also in this. So I said that I stated the upper semi-continuity theorem. Okay, then it tells us there is a supremum. So the supremum is achieved. So what is this supremum? There is a variational principle due to who, hua, and who. Okay, and it tells you can compute this supremum in the way you might expect. That is, you can define a topological entropy, which you can use a Bowen-Dinaburg approach. So you consider all compact subsets of any leaf of your foliation. You compute its entropy while you're looking at the distance along the leaves, okay? And you do the usual stuff. And it gives you some number. Actually, you can, like in the classical case, you can play with this definition, replacing lim sup with lim inf, replacing separated coverings by separating points or open covers. It's exactly parallel. Okay, and so they prove this definition. They identify the supremum of the F subordinated entropy, okay, by this topological formula. Okay, so one thing, the proof is written in the case of the unstable, the strong unstable foliation, but it applies to this, to uniformly expanding. In fact, two of them extended then to some non-linear lamination and also with non-uniform expansion, but with some assumptions that don't have the time to explain. So this is contained in that second paper. Okay, and it's also, they also extended to pressure. Okay, so if you know topological pressure, you can imagine, okay, and it works. Okay, so no. So I think maybe incredibly, okay, so I have, yeah, I'm surprised. Okay, so I think that's the last thing I want to say. So you have this unstable entropy. So this entropy subordinate to foliation. So now you can try to relate it, and it turns out that it's, because of the uniform expansion, it is related to, it is exactly equal to the growth rate of the volume. Okay, so this is what is written on the right-hand side. You take any compact disk contained in a leaf, okay, and you iterate it, and you compute the growth rate, and then you take the supremum over those disks. And it's actually the same as the topological entropy, and the proof is not very complicated. So I indulged into, this is the volume growth. So the bar is the volume inside the leaves. Okay, so you choose, you do the usual thing, which is you choose a Riemannian structure on your compact manifold, and then you can define the volume of disk inside the leaves. And this is that. Here it's a diffeomorphism, so we don't have to count multiplicities. So why? So first thing, the entropy is bigger than the growth rate of the volume. So let me think. So this is the point. Okay, so that should come from the continuity of the expanding foliation. Okay, what I wrote was that if you, so the topological entropy is given by this, you take these dynamical balls. Okay, now if you take the image, so you have a dynamical balls of order n, you take the image of that ball. It's contained, of course, in a ball of radius epsilon centered among, okay, where it should be. Okay, but then these volumes, they are bounded just because they are balls inside the foliation. The foliation is continuous, so, and the manifold is compact. So this is bounded independently of n or x. Okay, so this tells you, okay, let me see if I can say it correctly, that so entropy gives you a covering of you start with your disk D, okay, it will have a covering by epsilon n balls with diameter, with cardinality at most what is given by the topological entropy. Okay, and now you want to compute the image, the volume of the image of your disk, but this image of the disk, of course, is the image of the balls, of the previous balls, and so you get the number of balls times their maximum volume, which is bounded. So this is this inequality. Okay, this, what we just used was the continuity of the foliation. And now in the other direction, for the other inequality, what you do is that, so you want to prove that the volume growth is not smaller than the entropy. So you take one ball, which already has, so you want to find a disk which has big volume growth. Okay, so you take one disk which has big entropy. Okay, so that's just the definition of the topological entropy. You take a separated subset inside that disk. Okay, so its cardinality will be given by the entropy of that disk, which is almost the subordinate entropy itself. Okay, and now you see that if you, the dynamical ball around some point x contains, in fact, so the pre-image of a ball with a small but constant radius around the image. Okay, just because you are expanding, so if you pull back, it stays inside, it stays, if you are epsilon close at the end, you will stay close all the way. So of course it's expanding for some iterate, so this is why there is this constant little c, but that's not really serious. So you have every point, its dynamical ball it has in its image a ball of fixed radius. Okay, it's the other inclusion as the converse inclusion as the things we said first. And now you see that S is a separated set. So this tells you exactly that this, since the Bowen balls with half radius are disjoint, this is the separation property exactly, then their image, since we are working with a diffeomorphism, also are disjoint. And when you put this together, you obtain that the volume of the image is bigger than this number. Okay, I forgot to multiply by some constant. Okay, and you see there is a little subtlety, which is that I said that the image that if you pull back the Bowen ball, it is, if you pull back an ordinary ball inside the leaf, it is contained in the Bowen ball. Okay, that's the first statement of here. Okay, this is true, but what is not obvious and not always true is that this Bowen ball is actually contained in K0. Okay, so it may overlap a little bit. So there is a wrong direction to address this thing, which is to ask about the boundary. And then you get into a nice little problem that I could never solve. So let's not talk about it. But here there is a very simple solution that you don't have to get tied up with K0. You can just take a slightly larger ball. Okay, and then you will obtain the volume growth for this slightly larger ball, but this larger ball doesn't depend on n, so it still gives you, it still contributes exactly to the growth rate. Okay, and that gives you the other direction. So why is it very nice that the unstable entropy is the volume growth of the unstable foliation? Well, there are many settings. This is a simple one, where if you consider a hyperbolic automorphism of the torus, so it's already an Nosov, but you can see it as a partially hyperbolic one, so you can split some of the strongest exponent, not all of them if you don't want to say something too stupid. Then you get the corresponding strong unstable foliation. And what you can deduce from the above is that when you perturb your map, okay, the strong unstable entropy is constant. Okay, it would be completely obvious for the full entropy since you are structurally stable, but structural stability, I don't see that it says anything about the strong unstable foliation, at least not without some work. Okay, and this is, yeah, and so this actually comes from this paper. Okay, fantastic.
Other questions?
So for this exercise, even if we knew that we sent unstables to unstables, is this unstable topological entropy invariant under conjugacy of?
No, I don't think so. I'm not sure I have an example just now, but I don't see why.
Other questions? Right. Then we thank. There's one. Okay.
Sorry.
Can you go to the semi-continuity slide where you assume the expanding foliation? Do you think this is still true if you have hyperbolic foliation?
So you mean?
That you assume that f is uniformly expanding? What if you assume that f is uniformly anonsov?
I don't know. It's I don't know, but it's a good question. Better than the answer.
Oh, other questions? No?
I don't know if Federico was. Yes. You say it's the first theorem, the first serious theorem in the first part.
Okay. Other comments, questions? Okay. Well, thanks to Jerome.